Good afternoon to all the virtual attendees of this Sustainable Energy Futures 2020 conference. My name is Aaron Carver, and on behalf of my colleagues in the Data and Digitalisation group, I would like to thank you for taking an interest in our research topics today. Information is the oil of the 21st century, and analytics is the combustion engine. I think this famous quote is something worth bearing in mind throughout our presentation today. Now, the main objective of our presentation today is to demonstrate the power data has in suggesting, affirming, and actioning changes within the energy market. Hopefully by the end of this presentation, you will agree that data is indispensable in enabling the transition towards net zero. Now, whilst each and every one of our innovative research topics is unique, we all have the overarching theme of leveraging data to provide analytical insight and inform strategic decisions, thereby improving efficiency and reducing costs, accelerating the transition towards net zero. As we present our research topics, hopefully these benefits will become clear to you. To present our research in an intuitive and cohesive manner, this presentation is structured as a parallel to the UK electricity market. Starting at the top with generation, we have both myself and Amin, who evaluated data associated with electricity generation in the wholesale market. Following this, we have Benoit and Adriana, who looked at the potential for energy storage. Penultimately, we have Ronald, who looked at transmission and distribution. And last, but certainly not least, we have Lucy, who looked at data in the context of consumer engagement. If you do happen to have any questions, there is the opportunity to ask them at the panel session, which will be taking place following the conclusion of these presentations. So now, without any further ado, I will begin our presentations, starting with my research topic, a real options analysis exploring the value of flexibility in the UK's offshore wind industry. Now, I'm sure many of you may be thinking exactly what I was right at the start of my project. What does any of that mean, and why look at offshore wind? Well, let's look at the latter point first. The UK is the world leader in offshore wind, with over 20 gigawatts of installed capacity already. However, the current government have committed to doubling capacity to 40 gigawatts within the next 10 years. This means that on some windy days, the whole of the UK could be powered using solely offshore wind. As such, I'm sure you'll agree it is an extremely pertinent topic, and I thought it would be beneficial to do a real options evaluation on it. So, if we go back to real options for a second, what exactly is a real option? Well, a real option can be defined as the right, but not the obligation, to change a project or system in the face of uncertainty. For example, this could be waiting for the optimum time to expand a building, or perhaps sell an asset. In particular, I looked at the option of lifetime extension versus repowering, the possibility of abandonment in the event of declining electricity prices, and the option for contract for difference renewal. Looking towards the methodology, it began with an analysis of historic market reference data to develop a forecast of future electricity prices using geometric Brownian motion. Following this, a Monte Carlo simulation was used to sample thousands of possible future electricity prices. In each of these thousands of simulations, an exemplar wind farm's cash flows were modelled, and an evaluation of both the net present value and the expected government subsidies was provided. By then implementing decision rules into the model and rerunning the simulations, it was possible to determine if the flexibility provided by the real options would enhance the value of the projects. Using these results, I plan to make some comments on how UK policy can be adapted in light of this evaluation. So I'm sure many of you are asking, what exactly did I find? Well, real options do indeed improve system performance in the face of uncertainty. Looking at those target curves on the right, you can see how the system embedded with real options has reduced the value at risk and maximised the value to gain under uncertain electricity markets. However, perhaps the more consequential result I found was that projects under a contract for difference had a higher than expected net present value than those selling electricity on the wholesale market. This was owing to the cost of finance being substantially higher when not on a contract for difference. So, in essence, this means that wind farm operators should accept a contract for difference at prices substantially lower than the market price for electricity. However, this is also fantastic news for the government, as it means they would effectively be paying negative subsidies. Now, over a century and a half ago, Sir Arthur Conan Doyle wrote his famous character, Sherlock Holmes, impatiently shouting, "Data, data, I cannot make bricks without clay." These words still ring true today. It is hard to make effective policy decisions without data to support them. This research project helps provide evidence for them. This research reaffirms that the government should continue to hold contract for difference auctions for offshore wind to stabilize operator revenue streams. It also suggests that the option to extend contracts for difference should be provided to wind farm operators. So, in essence, what this project shows is that whilst real options would optimize the system in the face of uncertainty, it is preferential for both the government and operators to simply remove uncertainty with a contract for difference. Now, I'm well aware I've been talking for quite a while, so I'm more than happy to hand over to my colleague Amin, who conducted some very interesting and novel research into hedging using neural networks. Amin, please take it away.
Thank you, Aaron. The liberalization of the energy market has increased the role of financial derivatives in the energy sector. At the same time, the role of machine learning has expanded in the financial field in the last decades, thanks to the improvement in calculation capacities of computers and the access to large data. Therefore, big data and deep learning would enable energy companies to take better strategic and operational decisions in order to reduce their costs. My research project is about designing strategies to hedge financial risks in energy infrastructure projects using machine learning. The aim of the project is to apply a new technique called deep hedging to gas-fired power plants. But what is hedging? Hedging is an investment strategy used to reduce the risk of adverse price movement in a certain asset. For example, in the case of gas-fired power plants, we need to take many decisions like buying gas, running the power plant, and selling the produced electricity so that we can minimize the loss caused by fluctuations in the prices of commodities. What we actually do is that we use mathematical functions that have electricity and gas prices as variables, and these functions will give us certain metrics that determine the hedging decisions. Deep hedging, on the other hand, replaces these mathematical functions by a neural network that can provide better hedging decisions. So to apply deep hedging to gas-fired power plants, I first generated millions of electricity and gas prices paths using a Monte Carlo simulation. These paths will be used to train the neural network. Then I built a neural network that applied deep hedging to gas-fired power plants. This neural network will calculate the financial risks, then update its parameters, trying to minimize this risk. And after several iterations, the neural network will give us hedging decisions that minimizes the risk caused by fluctuations in prices of commodities. The most interesting part is hyperparameter tuning, where we try to find this network structure that gives the best results. Using the optimal hyperparameters, the neural network can give us hedging decisions that can keep the risk at levels lower than those given by the mathematical models. The next step would be to add frictions like transaction costs that are completely neglected by the mathematical models. And in this case, the gap between the neural network and the mathematical functions would be greater, and then the use of deep hedging more interesting. Many traders consider deep hedging as the start of a new era in finance. The results of this project show that it can also be the start of a new era in the energy sector. Thank you for your interest and attention, and now I will pass on to Benoit, who will discuss how data can be used to forecast the electricity load.
Thank you, Amin. Having finished with the electricity generation, we can move on to the electricity transmission network. I would like to talk to you about how data can be used to predict the electricity load 7 days in advance. Generating companies need to know with high accuracy how much demand is expected to schedule if generators have to run as reserve or full power to ensure security of supply. With the increasing installation of renewable sources, the load profile becomes much more variable because the sources rely on the unstable weather conditions. Forecasting the load with high certainty will thus become much more important in the future. My research projects presents three approaches to use machine learning models to forecast the load so that the companies can adapt to any unexpected changes. As a model is only an approximation, visualizing its shortcomings can be very beneficial. As the famous statistician George Box said, essentially, all models are wrong, but some are useful. And I want to use uncertainty to show which models are useful and which ones are not. For the first approach, valuable insights into the historic variability of the electricity load are gained. This is done by decomposing the data into a daily, weekly, and annual component. The analysis found that the historic load varies mostly on Monday mornings, but also on Saturday and Sunday evenings, as is shown in this figure. The second approach yields valuable insights into the training process of a machine learning model. For this specific example, a long short-term memory model is used that can be abbreviated by LSTM. A mean error and associated standard deviation are calculated. The errors are shown in orange and are plotted on top of the variability, which is shown in blue. You can see that there's a quite strong correlation between the two deviations, which also entails that the machine learning models have difficulties to predict regions of high variability. An energy trader can also use this plot to train a model for specific time intervals to make particularly good predictions on Monday mornings, for example. When a prediction is made, the standard deviation is then added to the actual forecast so that the energy trader is informed about the errors the model did during the training process. The third and last approach shows how probabilistic reasoning can be included in a model itself with Bayesian inference. In that case, the parameters in the network are randomly distributed so that each time a prediction is made, a different forecast is obtained. These output values can then be used to calculate a mean and standard deviation so that this approach does not rely on the statistical qualities of past behavior, which was the case for the first and second method. Unfortunately, the performance of the model is clearly inferior to the other machine learning models, so that in general, it would be recommended to use an LSTM model to make an electricity load prediction. The main advantage of all these approaches is that regions of extraordinarily high demand can be identified if they lie outside these regions of standard deviation. These spikes could potentially lead to large revenues, and my colleague Adriana will present you her main findings in that area.
Thank you, Benoit. The project I'm presenting here today is on prediction of electricity price, focused on outliers for battery storage unit applications. Machine learning techniques were used for these predictions, and the main findings of the project will be presented at the end. So battery storage units can nowadays be found at the transmission network. These assets have proven to be valuable to a smooth transition to a cleaner electricity system by providing quick responses at times when the grid is more unstable. Renewable supply cannot be controlled, and power can even be wasted at times where demand is low, unless storage is integrated, which allows correct management of the intermittent supply for renewables. Battery storage units, however, still face regulatory and economic challenges. The public and private sector contributions are required so deployment rates increase. Therefore, it is necessary to show these assets can be profitable. This is possible by trading electricity at the wholesale market. On this part of the grid, at the left of the figure, electricity is supplied with high voltages by generators and traded between the various participants. On the retail market, right part of the figure, electricity is supplied by energy companies to regular homes at lower voltages. Here the price is constant to consumers, but in the wholesale market the prices vary. This allows the participants of the wholesale market to trade electricity between low demand periods and high demand periods where the price is different. In the case of battery storage units, this will not only generate revenues, but bring support for the system operator when balancing the grid. The correct predictions of price spikes, or outliers in particular, can be very beneficial for these assets due to the high financial reward that it can provide. By looking at the best combination of inputs and models architecture, my research aimed to ease the entrance of new market participants by providing valuable insights for how to better predict these spikes or outliers. However, a spike should be defined first. So, what is a spike? There is no agreement on literature on from when does a price becomes a spike, but a recursive filter is often used. This consists of a moving average plus one standard deviation added on both directions. On this project, this filter was the delimitator between spikes and non-spiked regions, where models' performance was evaluated on both. Moving forward, the modeling consisted on giving inputs to various machine learning models, so the outputs could be generated. Firstly, it was found that the previous day price was one of the most valuable inputs for the model, which emphasized the daily seasonality of our habits, which therefore impacts the price of the wholesale market. In addition, the model benefited from the inputs from France. This provided the model with a sense of market integration. Due to the increasing volumes of load being transferred between the UK and France, it becomes necessary to consider it on price modeling for the UK. Considering the actual predictive model, my project found that hybridization could be beneficial for good predictions on both spikes and non-spike regions. Nevertheless, overall, the best performing model was long short-term memory, as my colleague Benoit also found out, a deep learning model which has shown great potential. This model showed the best predictions with a 1 day of memory. Nevertheless, the lowest root mean square error, which was the metric chosen, the lowest achieved in the spike regions was 52.3 pounds per megawatt hour, compared to the non-spike regions of 13.1. This emphasizes the hard task of predicting these outliers. I hope this short presentation allows you to understand the potential in integrating battery storage units in the electrical grid and how machine learning can be beneficial for these assets by providing good predictions, which therefore lead to revenues to these participants. Thank you for your attention, and next on the value chain is electricity distribution. So I'll pass on to my colleague Ronald to discuss the role of data and digitalization on increasing the visibility of low voltage networks.
Thank you, Adriana. Additional to the optimal use of transmission assets such as batteries, the transition to a net zero carbon economy will require the large-scale adoption of low-carbon technologies, such as rooftop solar PV systems and electric vehicles. The challenge is that most of these low-carbon technologies will be connected to low-voltage networks, a part of the electricity market that has limited visibility. The main objective of my project was to create an integrated tool that helps estimating the installed capacity of PV systems connected to low voltage networks, therefore increasing their visibility. The integrated tool combines three individual methods: aerial image analysis, reverse power flow analysis, and mean power generation. In the first method, high-resolution aerial images, such as the one shown in this slide, were used to identify PV systems. Then, the installed capacity of the PV systems was estimated using predefined technical parameters, such as the rated capacity of the PV panels. Needless to say, the accuracy of this method depends on the selection of the technical parameters. Nevertheless, one of the main advantages of this method is that it is not dependent on the orientation and the tilt of the PV systems. In the second method, an algorithm was developed to identify reverse power flow. Reverse power flow, or backfeed, is the flow of electricity from the consumers to the substation. In this slide, we can observe that reverse power flow is typically plotted with negative values. The maximum reverse power flow, circled in red, was used to determine the minimum installed capacity of PV systems required to overcome local demand. We found that this method worked best on feeders that had high PV penetration and were lightly loaded, since the impact of PV systems is more evident. In the third method, we use historical load feeder data, satellite weather data, and the orientation of the PV systems to estimate their mean power generation. The mean power generation was calculated by comparing the demand of days that had high irradiance and low cloud opacity against days that had low irradiance and high cloud opacity, which we can simply call sunny and cloudy days, respectively. This slide shows clearly the difference between the demand on a cloudy day and the demand on a sunny day. In conclusion, this research found that an integrated approach yielded better results because it relied on the strengths of each individual method and compensated for the individual weaknesses. Additionally, the integrated approach helped us find out that load masking can become significant due to the east and west orientation of PV systems. Finally, it is important to bear in mind that increasing the visibility of low voltage networks will enable a cost-effective integration of low carbon technologies. Thank you for your attention. Now that we have covered low voltage networks, we can move on to the next link of the value chain. Thus, Lucy will discuss how data and digitalization can be used to better engage consumers in the upcoming energy transition.
Thanks, Ronald. My colleagues so far have done a wonderful job demonstrating how data and analytics can help the industry accelerate the energy transition. Now we've come to the end of the energy value chain. I wanted to take a bit of time to talk about how digitalization can directly impact you, the energy consumers. So decarbonization and decentralization of energy have really transformed the roles of consumers. And while many have embraced those changes by installing solar panels and purchasing electric vehicles, a large portion of the energy users in the UK still remain quite disengaged. To tackle this issue, my project suggests that instead of relying on financial-based mechanisms, psychographics can help develop alternative means in delivering demand-side benefits. At this point, you may be asking, what is psychographics? Consumer psychographics include a range of qualitative traits, including your attitudes, value, and other emotional drivers that motivate behaviors. For example, where demographics may tell who you are as a consumer, psychographics will reveal why you have made a certain decision. Nowadays, our digital footprints are valuable sources for psychographic data, and this has been used for purposes ranging from personalizing your Netflix page to shaping voting behaviors. Given its impact in other industries, I wanted to understand how this can be applied in energy to better integrate consumer insights into our decision-making processes. Unlike my colleagues, I took more of a qualitative approach where I conducted interviews with subject experts and an online survey to understand the issue at hand from both an industry and consumer perspective. First, it was found that consumer psychographics can increase demand-side visibility. This can help resolve challenges Ronald had mentioned in his presentation, while also improving grid flexibility and competition in energy. This will allow policy and infrastructure planning decisions to be made strategically while stimulating innovation. All in all, this presents the opportunity to unlock benefits valued at more than £40 billion over the next couple of decades. Now, consumer psychographics are traditionally built on large volumes of personal data, but it was revealed that consumers are unwilling to share this information in exchange for energy services, therefore making data access the biggest barrier for psychographics. Results from the survey also showed that this unwillingness is directly correlated to levels of online privacy concerns that span across the digital landscape. Recent backlash against incumbent tech companies have decreased consumer digital trust, which makes them less likely to share data with lesser known competitors. It was found that the situation had disproportionately benefited these tech companies, allowing them to become data monopolies and stifle competition. Both of these are strong signs for market failures. Therefore, this research strongly recommends the establishment of an independent data regulator in order to allow psychographic innovations to emerge. The data regulator can increase digital trust and develop strategies for data sharing mandates to level the playing field. Since consumer data is generated across the economy, this data regulator should be cross-sectorial, and it is also recommended that this data regulator adopt a principle-based approach to keep up with technological developments. This way, regulators can identify the bad players quickly to ensure that the psychographic and other digital services are developed in a responsible and consumer-centric manner as we move towards a digitalized energy future. So from supply to demand, digitalization is seen to be disrupting every aspect of the energy industry, but also bringing immense value as we navigate through uncertainties brought forth by the energy transition. Going through the value chain once again, we first had Aaron, who used a real option analysis to show that whilst flexibility can enhance value in offshore wind projects, the use of contract for difference is preferential as they remove market uncertainties altogether, providing superior results for both the government and the operators. At the same time, Amin showed that by using machine learning and neural networks, energy companies can hedge price fluctuation risks and reduce costs for generation. Next, in a wholesale market, Benoit and Adriana showed data can be used to gain further insights into predictive models for both electricity load and price, allowing market participants to make strategic business decisions regarding their assets. Moving down to a distribution level, an integrated tool was developed and presented by Ronald to shine a light on PV systems connected to low voltage networks, which otherwise will be invisible to the network operators. Lastly, my project illustrated that while consumer psychographics can help realize demand-side benefits, a data regulator is needed to allow innovations to emerge and drive a consumer-centric energy transition. Overall, we showed that being able to integrate data and analytics into strategic decision-making processes will allow the industry to achieve net zero targets efficiently and in a cost-effective fashion. I hope that our projects have provided strong evidence that data and digitalization is imperative throughout the energy value chain and effectively demonstrated the message that information is the oil of the 21st century and analytics is the combustion engine. Thank you for listening, and we'll now see you at the panel session to take any questions you may have.